Hello students, good evening all. So welcome back to our next session. So in today's session we are going to start a new topic, linear programming. So this will be our last chapter in our 12th standard. So we have covered each and every concepts, every chapter. So this will be our last chapter which may
Hello students, good evening all.
so most probably we'll be having two sessions in this particular chapter of linear programming. So today is our first session. So first, meanwhile remaining students can join, I'll just give you a quick overview of what and all the topics are the concepts that we are going to cover in today's session of linear programming. So first, as usual, we'll just start with the basic part, that is the introduction. Right, in this introduction, it mostly comprises of the definition, the representation, what it is, and things like that will be covered in the introduction part. So the same thing like how we do with the regular things. So same like introduction will be involving comprises of all those terms, all those things, definition, representation, and those things will be covered. And then we'll be having, obviously it's a linear programming, there will be a solution or a methodology to simplify or get the answer. So this will be this graphical method to in order to get the solution, required solution. Right, so that's why we'll just dealing this graphical method. So in this graphical method, it comprises actually few theorems. So that also we are going to cover, like how we are going to do that. So in this graphical method, so there are two typical theorems. So which actually states our graphical theorem. Sorry, our graphical method. So we are going to discuss both of this theorem. Right, and then there is a standard methodology to follow to proceed in order to get our result here. So that method is nothing but corner point method. So in this corner point method, we'll be having some steps involved in it. So we are going to look each of the steps involved in the corner point method, and then we'll just pick up the points like each of the step by step, and then we'll just do our questions like to get the solution for the given equations. Right, so it's a very small chapter, so we'll just go step by step, we'll just go slowly. So as I mentioned in the introduction part, we'll just have a quick definition. So first, do you guys have so before getting into this, so do you guys have any idea regarding this linear programming? So if you guys have any idea, you can just let me know. Anything. So what it actually, because you have done linear equations, you have done solving different types of equations, right? So linear equation, quadratic equation, finding the solutions of them, right? Then what makes this a different part? So what is this actually a linear programming called here? So what is a typical difference you can identify once we are talking about a linear programming? So can anyone tell me? It could be anything. So whatever it that comes to your mind, you can just let me know. So anyone guys? Anything you want to say regarding this linear programming that comes to your mind? Okay, fine. So basically, what is this linear programming? So what is the typical definition here? So this linear programming is nothing but it's a problem. So basically the definition here, it's a problem of a maximizing or a minimizing a linear function. Right, so in general, finding the solution of a linear function or a linear equation, that you guys are familiar with it. But when we are talking about linear programming, it's nothing but here one word actually adding before our linear function, that is, it is a problem of maximizing or minimizing a linear function here. Right. So that linear function which we are actually maximizing or minimizing, that will also be subject to some linear constraints here. Right. So this linear constraint can be, they can be equalities, they can be inequalities. So that can be, the constraints can be anything. So there is a possibility that constraints may be equalities or the constraints may be inequalities. Right. So sorry. So but linear programming in general, it talks about the maximizing or the minimizing a linear function which is subjected to some constraints. So those will also be a linear constraints. Right. So the major idea here we should get here is, it's a maximizing or minimizing a linear function. So that is our basic definition of a linear programming. So let's just have a look of an example of this linear programming in order to understand what is a linear function which we are maximizing or minimizing, and that linear function will be subject to what linear constraints. Right, here I just in words I have mentioned that they will be subjected to some linear constraint. So you might wonder what could be those linear constraints, what happens. So those, to clear all those small doubts, we'll just have a quick example for a linear programming. So here is the example. So here you can see, find numbers x1 and x2 that maximize the sum x1 plus x2. Right. So here this is our major function which we are maximizing. Here they are talking about only maximizing. So here the sum of x1 plus x2. So this will be our major function, major linear function that we are going to subject to the maximizing, that we are talking about the maximization here. And this is subject to the constraint. So here if you observe, there are lots of linear constraints here. So one is x1 greater than equal to 0 and the other is x2 greater than equal to 0, and we are having three more here. x1 plus 2x2 less than equal to 4 and 4x1 plus 2x2 less than equal to 12 minus x1 plus x2 less than equal to 1. So these are our different constraints where this sum of x1 plus x2 is subjected to all these constraints which are mentioned here. Right. So x1 greater than equal to 0, x2 greater than equal to 0, x1 plus 2x2 less than equal to 4, 4x1 plus 2x2 less than equal to 12, and then minus x1 plus x2 less than equal to 1. Right. So here you can identify. So all these constraints here are inequalities. So there may be possible that I can have x1 plus x2 equal to 1, something like that. Or else there may be a possibility. I am not saying that it's exactly it should be a inequality in this constraints, but there may be possibility that there can be a equalities in some typical situations. But mostly we'll be having inequalities only. Right. So these are the constraints, linear constraints. All these five are the linear constraints which this linear function is subjected to. But here we have to find the problem of maximizing this sum of the function x1 plus x2. Right. So this is a typical example which gives us the difference of what is the linear function here and what are the linear constraints here. Right. So to give a clear discussion regarding the linear programming, so this example is all about it. So if you have any doubts in this example of understanding in this, what are the constraints, what are the function and all, you can please let me know before we move on to the further. Any doubts? Any questions regarding this? So I hope no doubts in this understanding of the difference between the function as well as the linear constraints. Right. So let's move on to the next one. So using this, amongst these linear constraints which our linear function has been subjected. So here we are having some classification in this constraints here. So let's see the classification. So here, sorry, this is x1 and this is x2. So here the first two linear constraints where the linear function has been subjected here are given by x1 greater than equal to 0 and the second one x2 greater than equal to 0. So these two are nothing but special constraints. So these two constraints here are called to be special because these are called non-negativity constraints. So here we doesn't have any negative. So x1 greater than equal to 0 which means positive and x2 greater than equal to 0 which means again a positive. Right. So these two are special because these are called no negativity constraints. And we can expect these two non-negativity constraints very often in our linear programming problems. Right. So these two first two are nothing but special because these are non-negativity constraints and these two will be found, these two will appear often in our linear programming problems. Right. So apart from these two, we are having three more constraints here. Amongst these three, so these other three are called to be major or main constraints. Right. So all these three are very important and all the other are main constraints. And amongst with these three, there is one constraint, there is one function which we are talking about whether we have to maximize or minimize. So that function is called to be the objective function. So for our previous one, we have taken x1 plus x2. We have to check the maximization for the function x1 plus x2, which states that this x1 plus x2 is nothing but called to be an objective function. Right. So very common that in a linear programming problem, we'll be having this non-negativity constraints. Apart from that, we'll be having some other main constraints where you can see here. I hope here it will be a plus, I think. So either it will be addition. So the addition will be the according to the example which we have seen here, because here this example state the maximum. So the maximum, the sum of x1 plus x2. Right. So the linear function which is related to this will become the objective function. Right. So here we have seen our basic standard function as well as we have seen the constraint and we have seen the classification amongst these constraints. So negativity constraints, main constraint as well as the objective function. Right. So we have all seen we have all done with our basic introduction part to our linear programming. So like the definition of it, the things related to it, the terms and the definitions related to each of these. Right. So everything has been covered. Right. So now let's move on to the next one, which is our graphical method here. Right. So as you guys can observe in the linear function, how many unknowns we are having. So in this entire example, if you observe how many constraints we are having, 1, 2, 3, 4 and 5. So we are having 5 constraints. And how many unknowns we are having? 2 unknown values. Right. So how can you solve this? So as we have only 2 unknown variables, we can easily solve this by plotting all these constraints. So we'll be easily finding the solution by using our graphical method, which means by plotting all these constraints on a graph. Right. So by taking our x and y axis, we can easily plot that. And then we'll be having the intersection region of all these inequalities, like all these constraints which we have here. Right. So that intersection region of all these is nothing but called an feasible region for the objective function. Because whatever we need there, that means either it can be a maximum value or the minimum value, both will be present in the feasible region only. Right, because it has to follow all the constraints which are mentioned, which means it is obvious that the answer will be lying in the intersection region of all these inequalities or nothing but all these constraints. So here for this particular example, we are having overall 5 constraints here. So how we'll be plotting this? So we'll be plotting all these constraints on our graph sheet or our axes x and y. Right, so once we plot this on our graph, then we'll be having a region which is the intersection of all these 5 constraints which are mentioned here. So the answer, either it can be a maximization or it can be a minimization. So both will be lying in that intersection region. So that intersection region here is nothing but called to be the feasible region for the objective function here. So what it is called here? So it is called to be feasible region for the objective function, because this region is the only region which satisfies the all given constraints here. Right. So it's easy that if for example we are having some x plus y equal to 5, some 2x plus 3y is equal to some 7. So how we will be getting the solution? You will just plot it. So the intersection point will be the solution of these two lines. Right. So same wise here, as we are having here, it is 2. So that's why we could easily get the point, intersection point. So as here we are having 5 different constraints, that too inequalities. It doesn't state exact equality. So those are maximum. Possibly they will be inequalities. So we'll be having a intersection region of all these inequalities, which is called to be the feasible region here, which satisfies all the given constraints. Right. So let's see the theorems related to our graphical method here. Right. So let R be the feasible region. So as I mentioned, what is this feasible region called to be? So this is the intersection region of all the constraints. Right. So let R be the feasible region. So in general, it will be a convex polygon. So in general. Right. So for a linear programming problem, and let z equal to ax plus by be the objective function. So can you guys tell me what is this objective function just now we have discussed? So what do you mean by this objective function, guys? Quickly, anyone? In your own words. So you can let me know in your own words. So this objective function is nothing but the function which we are subjecting or finding the maximum or minimum. Right. So that will be our main function here, and the others will be our constraints. Right. So here that function we have considered here z equal to ax plus by. So this is our, yes, Shivaranjani has already given function to be maximized or minimized. So exactly. So objective function is nothing but the function which is either subjected to maximum or minimum. In some cases what happens, they will be asking both. So both maximum and minimum can also be asked. Right. So when z has an optimal value, that is it can be either maximum or minimum, where these variables x and y are subjected to constraints described by the linear inequalities. So this optimal value must occur at the corner point of the feasible region. Right. So here the condition will be, so if for example I am having this entire region something like this. For suppose I am having this to be my feasible region. So how can we take, so we have to take all these points in between and we have to check, then only we will be getting the maximum and minimum. Right. But here this theorem states that the optimal value, that means the maximum or minimum value, must occur at the corner point. So you will be taking only the corner points. So how many corners here we are having? 4 corners. So it will be okay if you check only these 4 corner points of this entire feasible region. So there is no need to take all these points which are present inside the feasible region here. So if we have to take like that, so we cannot actually solve the linear programming problem there. Right. So this theorem here states that when we have the function z equal to ax plus by, if that is our objective function, and here we have to find our optimal value, which is either a maximum or the minimum. Right. So the optimal value will always be, must be, so it must be occur at the corner point of the feasible region. So it indirectly states that there is no need to check all these inside points here. So you can directly take the corner points of the feasible region in order to check the maximum or the minimum value of the function here, of the objective function here. Right. So let's go back to our next, move ahead and see our next theorem. So let's let R be the feasible region for a linear programming problem, and let Z equal to ax plus by be the objective function. If R is bounded, then the objective function Z has both a minimum and maximum value on R, and each of these occurs at the corner point. Right, so here we have to check whether it's bounded or not. Right, because in a closed figure only we will be getting the corner points. So if it's a bounded, then both the maximum and minimum will be occurred at each of the corner points. So it can be any of the corners, because it doesn't state that it will be only one corner. So any of the vertex, it can give, one can give the maximum value, and the other vertex, that is the other corner point, can give the minimum value. Right. So here let's see the example. So let's see the example which we have seen in our starting. So what are the constraints which they have given there? So let me check it once. So all are less than equal to inequalities. So first non-negative are common. So let's just write them first. x1 greater than equal to 0 and x2 greater than equal to 0. So these two are nothing but our non-negative constraints which are special, and the other three constraints which they have mentioned are 4x1 plus 2x2 less than equal to 12, and then minus x1 plus 2x2 less than equal to 4, and the other minus x1 plus x2 less than equal to 1. So these are the 5 constraints which they have given. So now what we have to take? We have to take the intersection of all these. Right. So first x1 greater than equal to 0. So let's take this to be our x1 and this to be our x2. Right. So x1 greater than equal to 0. So this means this part. Right. And x2 greater than is equal to 0. That means this will be the other part, which means both are positive in the sense it will be the first quadrant, because we are here considering our x and y, x1 and x2 to be our axes in order to plot the graph and get the answer here. Right. So x1 and x2 here. So x1 greater than equal to 0. So this part, and x2 greater than equal to will be the this part. Right. So here x1, x2. So now let's first two non-negative constraints are already over here. That states that only first quadrant we have to consider here. So let's check the next constraint here. 4x1 plus 2x2 less than equal to 12. So we have already seen whenever we are having an inequality, how to plot the graph of it. We'll consider that to be an equality, that is 4x1 plus 2x2 is equal to 12, and then we'll plot the graph. So I hope the graph of this will be, so this will be the line 4x1 plus 2x2 12. So this is the line. So here the inequality is less than equal to, that means this entire region. So this entire region will be the region of this inequality, which is given by 4x1 plus 2x2 less than equal to 12. So in the similar way, we have to plot the second inequality, that is fourth inequality, that is minus x1 plus 2x2 less than equal to 4. So here you can identify that. So again, that is also less than, so this entire region. And the last one, minus x1 plus x2 less than equal to 0, that will be this line, and this region contains this entire thing. So if you observe, all these three intersection will be only this shaded region. So this region will be our feasible region, which is the intersection of all these 5 constraints which are given here. Right, so as we have seen, according to the theorems which are stated in our graphical method, either it can be the maximum value or the minimum value. It will be at the corner points here. Right, which means how many corners we are having here. So it will be 1, 2 here, 3 here, and you can take 4 and 5. Right. So we can simply take the corner points and then we can check the optimum value of our standard function, that is z equal to x1 plus x2. Right. So let's see the corner point. So here you can see one corner point will be 0, 1. Right. So that is this point, x is 0 and y is 1. So this is 0, 0. We can neglect that. So let's take this also 0, 0. It will be 0 only. And the other 0, 1. So the corner point x1 will be 0 and x2 will be 1. So here our function here is x1 plus x2. So that value will become 0 plus 1, 1. And the other is x is 3 here, whereas y is 0. That means 3, 0. The maximum value here of x1 plus x2 will be 3. And the next point we are having is 8 by 3, 2 by 3. I hope it will be here. So 8 by 3, 2 by 3, 1 point, and the other will be 2 by 3, 5 by 3. So these intersection points you can find by taking the equations and simplifying it. So you can see the sum of these two will be 10 by 3 and the sum of these two will be 7 by 3. So these are the only corner points. So it will be enough if we check only the corner points here. Right. So amongst this sum, which is the maximum here? This is our 3 point something. So the maximum corner point value will be x1, x2 is equal to 8 by 3, 2 by 3. And the maximum value is nothing but 10 by 3. If suppose if I asked you for the minimum, then it will be x1, x2 value will be equal to 0, 1. Sorry, minimum will be this 0, 0, right? So 0, 0. And the minimum value will be 0. Right. So likewise, if we could able to plot these graphs of all the constraints, and if we could easily, then if we can actually identify the feasible region, then we can go by taking the corner points in order to get our optimum value, which it can be a maximum value or the minimum value. So this is our example that I have just shown you in our beginning of the session for our linear programming. So now let's see the steps of solving this linear programming. Right, so this just now we have seen the plotting and all. So this method of solving linear programming is nothing but referred as a corner point method, because here we are only considering the corner points, which are nothing but the vertices of the feasible region, and we are obtaining our required optimal value, whether it could be a maximum value or the minimum value. Right, so that's why here this method of solving this linear programming problem is referred as a corner point method. So let's see what are the steps involved here in order to solve our linear programming problem using this corner point method. Find the feasible region of the linear programming problem and determine its corner points either by inspection or by solving the two equations of the lines intersecting at the point. Right, so here we have already plotted the constraints and then we have identified all the corners of the all the corner points here, which are nothing but the vertices. So how you can find? If we are plotting exactly to the scale, then you can identify the vertices by inspection. If not, you can see what is this vertex point, like which intersection of two curves or the two constraints is this vertex here. Then you can take those two and you can solve the equations in order to get the corner point here. Right. So in overall, our first step in order to solve the linear programming problem is plot the constraints on the graph and identify the feasible region of the linear programming problem and try to determine the corner points of the feasible region. So this is our first step in order to solve the linear programming problem. And the next one here is evaluate the objective function, that is z equal to ax plus by at each corner point. So we cannot neglect any of the corner point here. We have to evaluate the given objective function at each of the corner points. Right, so let capital M and small m respectively denote the largest and smallest values of these points. That means this is maximum value and this is minimum value of the objective function here. Right. So when the feasible region is bounded, M and M are, capital M and small m are the maximum and minimum values of set. Right. So what happens if it is unbounded? If it is unbounded, then M is the maximum value of Z. If the open half plane determined by AX plus BM, BY greater than M has no point in common with the feasible region, otherwise Z has no maximum value. So if it is bounded, there is no issue. We can directly get our maximum and minimum values. If it is unbounded, then the maximum value we have to check by the condition, that is AX plus BY greater than M. Right. So if it is a half open, half plane determined, otherwise there will be no maximum value. That means there is no point here which gives the maximum value. So that we have to remember. Right. So and the same way for the minimum also. Right. So M is the minimum value of Z if the open half plane determined by AX plus BY less than M has no point in common with the feasible region. So there should be a common point with this equation to the feasible region. Right. If it's only unbounded. If not, there is no minimum value also. So you'll be getting this once we start doing this question. So there is nothing to worry. But the only thing you have to remember here is first step, plot the graph and identify the feasible region and then try to figure out the corner points and then evaluate our objective function at each of the corner points and then try to predict the maximum and minimum values, which are the optimum values of our given function Z, given objective function. So just now we have discussed the methods or the steps involved in our corner point method, and we have already seen one example. So let's do a question here related to this method of solving our linear programming problem. So here comes the first one, guys. Solve the following linear programming problem graphically. So the question here is maximize Z equal to 4x plus y, which means what is our objective function here? So the objective function which is given here is Z equal to 4x plus y. So subject to the constraints. So here constraints are already given. So the constraints which are given here are x plus y less than equal to 50, 3x plus y less than equal to 90, and then x greater than equal to 0, and then y greater than equal to 0. So now try to figure out this linear programming problem and try to find the answer. So here I have mentioned it should be a maximization, not a minimization. So for the objective function, it should be a maximization. So give it a try, guys, quickly. So I hope you guys are familiar with this plotting of graphs and all, because you are doing this since the 9th or 10th standard. So you have to be confident enough to do this. So what are the first step, guys, in order to solve this linear programming problem? So the first step here is to plot the graph of this all given constraints and identify the feasible region here. So if you guys have any doubts, so please do that comment in the comment section. I'll just checking the comments frequently. Okay, Arun already plotted it. Okay, fine. So if Arun, you already plotted it, can you just identify the corner points also? So let's plot the graph here. So the constraints we have to plot here. So these are the constraints. So let's take the x and y axis. So let's take the constraint here, x plus y. So here the inequality less than equal to 50. So we can take x plus y equal to 50. Right. So let's take the gaps intervals as 10, 20, 30, 40 and 50. Right. So for the graph, so first one here, x plus y equal to 50. That means when x equal to 0, y is 50. So 1, 2, 4, 5. Sorry. So y is 50 somewhere here. And the other will be here. So this is the plot here. Right. So this is the plot of the constraint x plus y equal to 50 and less than means, so this will be the region. Right. Because for these two, x greater than equal to 0 and y greater than equal to 0 states that it will be obviously in the first quadrant. Right. And then this constraint is already plotted. And the next constraint we are having is 3x plus y less than equal to 90, which means 3x plus y equal to 90. When x is 0, y will be 90. That means somewhere here I am just plotting it. Right. So when x is 0, y will be 90. And when y is 0, x will be 30. That means here. So this graph will be, the plot will be like this. Right. So what is the feasible region now? So this will be the feasible region. Then what are the corner points? So this will be the one corner point and this will be the other. X is 0, y is 50. And this is the other, x is 30, y will be 0. And this is 0, 0. And the other is this point. which we have to find the intersection of these two linear equations. That is x plus y equal to 50 and 3x plus y is equal to 90. So let's just solve these two equations. So 3x plus y is equal to 90. I'm just subtracting it. So 3x minus x, it will be 2x. So this will be 0. Equal to 90 minus 50, it will be 40. And x will be equal to 20 here. So when x equal to 20, so what will be y? So y will be equal to 30. So this intersection point, so another corner point will be having the coordinates 20, 30. So now we have derived our feasible region as well as we have figured out the corner points here. Right. So the four corner points which we have here is 0, 50, 0, 0, 30, 0 and 20, 0. Right. So let's just erase this. So our corner points, that is x, y. One column. And the other will be our maximization objective function, that is equal to 4x plus y. So here the first corner point we are having is origin, that we have seen 0, 0. Then what will be the value here? So x will be 0, y will be 0. So that means the value will be 0 only here. And the second corner point we have seen is when x is 30, y is 0. So let's substitute x30 here, that is 4 into 3, 12. 120 plus 0, that means 120 only. And the third one we have seen is x20 and y30. So x20, that is 4 into 2, 40, 80 plus 30, which is equal to 110. And the fourth corner point which we have seen is, when x is 0, y will be 50. That means this value is 50. So amongst all these, what is the maximum value? So here we are trying to figure out the maximum value but not the minimum. So the maximum value here is 120. Right. So by solving this, the maximum value of this objective function z equal to 4x plus y is equal to 120. So I'll write here. So maximum value of the objective function z equal to 4x plus y is 120 at the point 30, 0. So this will be the solution of the given linear programming problem. So I hope many of you has already solved it. So this will be the objective function which is z equal to 4x plus y. So for that only we have So can you guys check the answer? If you have any doubts, you can let me know. If not, we can just move ahead with our next question. Quickly check the solution here and compare your answer. If you have any doubts in this, you can just let me know. Okay. Do you have any doubts, Arun? So you can let me know. So what's your doubt? Okay, done. Okay, fine. So let's move on to the next one. So I have explained you this one clearly. So I hope you guys can do this second problem related to our linear programming. So this one you can just solve this question and let me know. So solve the following linear programming problem graphically. That is, you have to find the minimize here. So just in the previous question, we have done the maximization. So now this question is related to the minimization. But the procedure is the same and the steps involved also the same thing. So I hope you guys can do it. So quickly find this and let me know the minimum value and at what vertex, at what the corner point the minimum value has occurred. So quickly guys. So the objective function which is given here is z equal to 200x plus 500y. So this is the objective function which is given here guys, and this objective function is subject to the constraints which are mentioned here. So the first constraints are non-negative constraints where x greater than equal to 0 as well as y greater than equal to 0, and the remaining two constraints which are mentioned here are x plus 2y is greater than equal to 10, and the next 3x plus 4y is less than equal to 24. So first you have to plot the graph using these four constraints, and then find the feasible region and then try to figure out the corner points here. So just be careful while doing this plotting of the linear equations, because once we done some error in this plotting itself, then the entire solution will be wrong. So we have to be keen and we have to pay attention while doing this plotting only, because once we plot it carefully, then the rest will be the easiest one, because once we plot it, we could easily identify the feasible region and then we could easily find the corner points, and we'll be substituting the points in our objective function in order to get the maximization or the minimization of the objective function. So if anyone done plotting the graph, you can let me know. And we'll see what are the corner points. Anyone has done, guys, plotting of the graph here? So let me take the axis first. So as we know, the first two non-negativity constraints state that it will be in our first quadrant itself, x-axis and y-axis. So x greater than equal to 0, so this part. Similarly, y greater than equal to 0, this part. So it will be obviously located in the first quadrant itself. And then we have to plot the other two constraints here. The first one is x plus 2y greater than equal to 0, which means x plus 2y equal to 10. And the other one is 3x plus 4y less than equal to 24, which is nothing but 3x plus 4y is equal to 24. So now we have to plot both of these graphs of these two lines here. So let's take x equal to 0. If x is 0, y will be 5. That means somewhere here. Let me take somewhere here. 1, 2, 3, 4, 5. Okay, here. This is the point where x is 0 and y is 5. Right. And what happens when y is 0? Then it will be x equal to 10. That means 1, 2, 3, 5, 6, 7, 8, 9, 10. Somewhere here. So this is x is 10 and y equal to 0. So this is the plot of the constraint here, that is x plus 2y equal to 10. So let's go for the next one. So let's take x equal to 0 here. That means y will be 6. So somewhere here 0, 6. Similarly, take y equal to 0. That will be 8. X will be 8. That means here. So 8, 0. So now according to the plot, what will be the feasible region here? So the feasible region here will be this portion here. Because for this only, here you can see x plus 2y greater than equal to 0. That means for this graph it is greater than, that means above part. So this is the above part, and this graph it is less than equal to below part. That means this is the below part. So the feasible region of all the constraints is given to be this shaded portion, where the one vertex, one corner point is 0, 6, and the other corner point is 0, 5, and the other corner point is the intersection of these two lines. So let's find the intersection here. So I'm just multiplying this with 2. 2x plus 4y is equal to 20, and 3x plus 4y is equal to 24. So let's just subtract. 2x minus 3x minus x, 0. 20 minus, so it will be minus 4. That means x will be 4 here. Right. So here x will be 4. So if x is 4, what about y? It will be 3. So the other corner point or the vertex here is given to be 4, 3. So now we have found out the feasible region as well as the vertices, that is the corner points. So the corner points are 0, 5, 0, 6 as well as 4, 3. So let's erase this and draw our table here. So corner points here, x, y. And then our objective function. So here we have to find the minimization of the objective function, 200x plus 500y. So first corner point 0, 5. That means x will be 0, y will be 5. That is 5 5s are 2500. And the next corner point is 4, 3. X will be 4. 4 into 2, 800 plus 3 into 5, 1500, which is 15 plus 5, 23. So 2300 here. And the last point is 0, 6. So x will be again 0, y will be 6. So 5 into 6, 30. That means the 3000 here. So here we have to find the minimize. So what is the minimization of the objective function here? That is the minimum value here is 2300. That means minimum of the objective function z equal to 200x plus 500y is given by 2300 at the vertex point 4, 3. So this will be the solution of the given linear programming problem. Right. So this is how we can find by plotting the graph, right, for any given constraints here. Right. So now I hope you guys have understood how to apply the methodology of our corner point and how to get the solution of the linear programming problem here. Right. So I'll just now we have done one question related to the minimization and one question related to the maximization of the objective function. So now I'll just give you a question for you guys as a homework. Okay, where is the homework question? Yeah. So you can take this question to be a homework question here. So this is the question for homework which involves both the minimization as well as the maximization here. So you can work it on this question as a practice because in today's session we have already done 2 questions. So if you could able to solve this, it will be the practice question for you guys. So that's all for our today's class of linear programming. So we'll be having most probably only one more session in this particular chapter of linear programming. So in that we'll be discussing the different models of questions we can expect in our linear programming. Right. So that's all for today. So if you have any questions, you can let me know. And if not, we'll just wind up our session today. So I hope no one has any doubts. Okay, fine. So that's all for today, guys. So thank you. Let's continue the rest in our next session of linear programming. Thank you.